So remember, we're now visiting Sir Isaac Newton. And Sir Isaac Newton solves the first problem for us for being able to figure out what time is. You need calculus in order to... Do you want me to turn some lights on? Or is it too dark, or do you like it? How about that? Is that okay? He creates calculus in order to determine instantaneous velocity, but then you need a theory of space and time in order to subsume your formulas and be able to make sense of what time is. And so you have two options here, absolute space or relative space. And remember, Newton says that absolute space is a little bit like a container. So absolute in the sense of kind of like objective. There's an objective reference point that you could actually say this object, this planet, is below, or this person is below this person. In relative space, we can't say that because it depends on, everything's relative. There's no kind of God's eye point of view in which you could say this one's absolutely below and this one's on top. It depends on where your perspective is. From here, this is going to possibly look below or to the right or to the left. That would be relative space. So we have to figure out, how do we tell? And we talked about two problems that arise. It just seems practically impossible to be able to ever create a rocket ship that could go outside of the universe and get a God's eye point of view. And the second problem that was insurmountable is that, well, if the universe simply means everything that exists, every time you try to go outside of the universe, you're just making more universe. In fact, this is exactly what the Big Bang suggests, is that the universe is expanding. It's expanding to what? Into nothing. There's nothing on the other side. Everything that exists is within the universe. And so you can never really get outside of the universe. Therefore, I asked you to think about, from last class, do you think that you could come up either with a scientific empirical experiment or perhaps even just an a priori thought experiment in which you could tell which universe we were actually living in? You said yes last class. Do you have an idea?
No, but right now I'm just thinking, like, if we all experience time the same, would that have something to do with it?
Well, first, remember, time is going to depend on motion. Motion depends on there being space. So first things first, let's just get the space worked out. Well, Newton believes that through his famous bucket experiment. Now, this is not an actual scientific empirical experiment you could do in the lab. Okay? It is a thought experiment. And what's nice about thought experiments is that you can isolate all the variables and derive a fact theoretically to import into the empirical world. So, for example, it almost starts like a riddle. Like, you have a block of ice, a rope, and you've heard those riddles. Well, in this, you've got a bucket, water, and a rope. I'm going to use this chair here as a prop. Now, why wouldn't this work empirically? Well, because obviously the rope would have to hang on something. Now, in Newton's thought experiment, you only have three things. The rope, so it's not hanging on anything. You're just conceiving that it's supporting the bucket, and in the bucket is water. So if I take that bucket and I start winding, the motion of the bucket is going to be transferred up into the rope. And you get all that kinetic potential energy stored up, and you start to see the rope get twisted, and then it's all being stored in there, and it's going to get harder and harder to twist And then what happens when you let go? The motion that's stored, the kinetic energy that's stored in the rope is now going to be released because there's nothing preventing it. And that's going to be transferred to the bucket. And the motion's now in the rope and in the bucket, but not the water yet, until it starts, the motion of the bucket starts to transfer into the water. Now the water is moving, and just like the experiment of centripetal force, where you take a tennis ball onto a rope, and you do this, and you're swinging, you're giving it two motions, an outward, but it also has, a sideways motion, so you're going like this, but it's also pulling outward. If you were to let go of that, what would happen? It would fly out. Well, likewise, the water is given this circular orbital motion. And the water wants to go out, but it's prevented by the bucket. So what you start to see is when they're all moving together, now the water's going to start to go concave and start to move up the sides of the bucket because it's wanting to push outwards, but it can't go through the bucket, so it starts to move up. Now remember what motion means. Change with respect to something. Moving with respect to something. So we're going to take it granted the assumption that, yes, at this point, the rope, the bucket, and the water are all moving together. Here's where Newton's question comes. Why is the water becoming concave? Or let me retranslate that. The water is moving with respect to what? Because we're assuming it's moving in the thought experiment. But because motion means a change with respect to I'm moving away from or moving towards, we're assuming that the water clearly is moving with the bucket and rope. What is the water moving with respect to? Gravity doesn't exist in the thought. You only have three things to choose from in the thought experiment. What's that?
Water is moving within itself.
Well, you're conceiving the whole water moving together. So it's not changing with respect to itself. It's like, for example, if you start spinning around, and I say, oh, you're moving with respect to what? You wouldn't say with respect to myself. It's like, no, myself is moving. So the water's moving by assumption, by presupposition. Well, what is it moving with respect to? Because that's what motion means, to change with. Well, that's interesting. So if you're driving in a car, do you say that I'm moving with respect to my car or I'm moving with my car?
Well, like if I'm getting out of my car, I'm maybe moving with.
Yeah, if you jump out of your car.
The water's trying to get out of the bucket.
But it hasn't done that yet. So, for example, I'm the water. Okay, am I moving with, whoa, that made me dizzy. Am I moving with respect to the bucket, or am I moving with the bucket? With the bucket. So that's not going to work. And here's my rope. Okay, they're all moving together. They're not moving with respect to each other. If you're driving down Chapman and you say, I'm moving, you don't say because I'm moving, changing with respect to my car. You're saying my car and myself are moving or changing with respect to the campus. I'm moving closer, I'm moving farther away. I'm changing. Clearly it's moving. Now, remember, you only have two options in which to conceive of this experiment. And therefore, Newton's making a sort of reductio ad absurdum. Remember, a reductio says either A or B. Either A or B. If you consider one and it ends up becoming nonsensical, or you end up in absurdity or contradiction, you know that can't be it. It must be the other. So you can conceive of this experiment either in this framework or this. You have to ask yourself, well, which one does it coherently and consistently make sense? The bucket, the rope, and the water are all moving together. They are moving. Therefore, the water and bucket must be removing with or changing with respect to something. What's the something? Did we allow error in the experiment? Think about it this way. Take everything out of the room and start spinning around. You're moving with respect to what? So you have no more objects to reference. What kind of space? Okay. Now think about that in terms of the room. How do you define space? The space what?
Limited by walls.
Yes. Therefore, where does this thought experiment make sense? In this scenario or this scenario? Bingo. Here it would be nonsensical because you'd say it's both moving with respect, because moving means change with respect to something, but there is no something to move, so you have a contradiction. This is the only scenario in which the thought experiment of the bucket and water actually moving would therefore consistently be moving because it's changing with respect to absolute space, which is conceived to be a container. Therefore, we know empirically, Newton says, we live in absolute space. Now you've got an objective reference point. And remember, we said the difficult thing about motion, remember the train or the car, is we can never kind of get an objective God's eye point of view. And then we talked about the practical and the theoretical problem is you couldn't even get outside of the universe to conceive and see it from a God's eye point of view objectively. What does he do? He uses mathematics and thought experiment to, rather than physically move you out to the universe, to draw your mind outside to now be able to see that in fact the universe is absolute space. Now he can build his physics. So all mechanical physics comes from Sir Isaac Newton. That means that the inverse square law, that means also the law of gravity, centripetal force, all those laws apply equally to every single object in the universe. Mathematically, you don't have to reconsider your mathematics every time that you talk about a different referent object. That is the brilliance of Newton. He's drawn your mind up into the mind of God and is using mathematics to describe objectively the way the mechanics and motion of the universe works. Pretty amazing, isn't it? Question? You had a question?
Yeah. So can you explain again how the edge is defined in the absolute space?
He says that it's analogous to something like a container. Because I don't think he actually thinks that, yeah, you just fly out there and you'll run into like, oh wow, here's the edge of the universe. So what he says is that, well, in order to have something to be absolute, it has to be contained in a sense. Contained by what? The universe, the kind of the absolute reference frame. And he says, if it helps, think of it like a container. But in this, so you have, where's the space? The space is between everything, like you said, the room. If I took everything out of the room and put you in the middle, how can I say that's the middle? It's the middle with respect to the reference of the walls.
So if there were like in the relative space universe, there's like infinite amount of points. Wouldn't and like it was laid out in a grid? Wouldn't if you were in the middle,
Yeah, there would be no, there's no absolute, reference.
Like,
Mm-hmm.
choose, say, like, in respect with, to, like, the whole, all the points, you're...
Yeah, you couldn't actually say, I'm absolutely in the middle. It's like, well, it might look like you're from the middle from this point of reference here, but you come over here, and now it looks like you're out. So you're absolutely right. That's why Newton believes, no, you need to be able to argue for and prove the absolute space.
It might just be me, like, trying to put myself as the center of the universe, but in relative space, would we also not be considered our own center of the universe at that point? From our perspective, at least?
Yeah, that's right. You couldn't objectively say that this is the center. It's like it might look from the center from your perspective. Change your perspective, and it looks different. Just like the train scenario. Change your perspective, and it's going to look different. Now, this is going to open up for Einstein's relativity, but first, let's talk about a contemporary. We'll switch over from science to philosophy. Immanuel Kant, the Prussian philosopher, thought about space and time something different. Because notice that Newton and most physicists think of space and time as something out there. If you ever watch like the Discovery Channel or something on TV, it makes it seem like time is something out in the universe flowing. Well, Immanuel Kant says to the question, well, what is space? Space is not something objective. Remember, something can either be within the subject or it can be observer independent is objective. He's saying it's not that stuff. It's not stuff outside of your mind. It's not objective and real. Is it a substance? Can I pour time into a glass and drink it? Remember what my nephew said? No, you can't. Is it an accident? That's that Aristotelian language. An accident is a non-essential property. The color of your eyes, the color of your skin is not essential to your essence of being a human being. You can change it and still be a human being. So he's saying, well, time's not an accidental property either. Well, what is it? Is it a relation? Because you can have left and right. That's not a relation, he says. Instead, it's subjective.
Wouldn't the present and the past be relation? Present time and past time and future time?
Yeah, but that's not time. A person isn't time. And then that brings up the whole question whether do people even exist in the past and future? Are there actually people that you could go find in? I thought the past doesn't exist because what exists is what is. Right? If you said, what's real? What is? What it's now? What exists? What is the past? What was? It's not anymore. What's the future? It's not yet. Yeah, so this is this kind of A theory of time that the only thing that's real, there's like a place called the future in the past that you could go to. They're gone. The only thing that exists is the present. That's kind of a theory of time and philosophy of time. Well, he says, look, it's subjective, meaning it's in you. It's nothing to be found outside of your mind. Therefore, it's ideal. It's dealing with your ideas. Well, where does it come from? It originates from your mind's nature. Now, this answers the question of, if it's just subjective, remember the taste of coffee? Does everybody like the taste of coffee? Do people like chicken hearts? How many people like chicken hearts? Liver? Okay. See, everybody's different because it's subjective. They experience it differently. Well, if time's subjective, how the heck do we all have the same time and get here roughly at the same time? Welcome. Thank you. Yeah. Sure, leave it there. But they probably know that they're late. It's not like you actually thought that we're talking about time. It's not like you actually thought we were getting here at 2:15, and it ended up being different subjectively from everybody else's perception. We all have a kind of objective. Doesn't that seem to be a problem? Why aren't we experiencing time differently if it's subjective and ideal in your mind?
I always thought about it was that our time is like kind of trivial in the fact that, I mean, on the grand scale of things, our time is very, it doesn't really, we created time basically to be able to tell somebody, hey, I'm going to be here at this time, we should meet there.
So we all agree to this convention. Maybe. But that doesn't tell you how you experience it. Yeah.
Again, the phrases like, "Oh man, that was the best day of my life," or "That was the longest day of my life." Those show that the way that we perceive time, at a psychological level, it can be different based on our experiences. So I think in the way that we measure time passing,
So you're saying you can experience it differently, but the measure of it,
you can be at the same event.
we all agree to.
And they're all going to perceive the like how time, whether it was good or bad, differently. Like how long it's been.
But it's interesting, if you put them in the same context of having fun, they're going to experience it the same way as you do. So maybe not everybody,
This would be personal in the fact that one person might think an hour has gone by while another person would think 45 minutes has gone by.
Well, Immanuel Kant says that the reason why there's uniformity is because, so long as you're not taking like psychedelic drugs or something, which will really alter your perception of time, or, any kind of like messing around with the brain, brain damage or something like that, schizophrenia, as long as we're sharing a common physiological structure within the brain and mental structure, time, he says, or space, originates. That's a better one because we could differ in time, but why do we have the same concept or experience of space? That's better. Because he says it originates from your mind's nature. So as long as you're not tweaking the nature of your mind, either through drugs or some maldevelopment within your mind, you're going to have something like a stable law is a scheme. Now, a law is, well, take, for example, something very easy. When you see a red light, what does that mean? If there's a red light, you put on the gas and try to, oh, that's yellow lights. Yeah, that's slow down, speed up, try to make it through the, right? Or what's the saying? No cop, no stop. Yeah. Well, law is always put into a conditional of if, then. If X, if you see the red light, then Y, then stop. According to Immanuel Kant, your brain works that way for organizing and coordinating everything that's sensed. Because Immanuel Kant believes he's inherited this kind of Humean empiricism from his predecessors that believe part of modernity is a rejection of Aristotle's philosophy and metaphysics, and specifically the idea that there's teleology or forms and essences in nature. What you get is the modern scientific view of a mechanized world. Really, all you have is, well, think about it this way. Does modern science say that there's actually the quality of red in this pen? No, they put it in the world is black and white. You just happen to, when the wavelength, if you have a wavelength of 900 nanometers, hit your eyeballs, Your brain is, according to Kant, structured in a law-like scheme. If 900 nanometers hits your eyes, then produce the phenomena of red. But look, there's no red in the apple. It's simply just molecules. If you zoomed in, this is the modern scientific account. It comes from this kind of stuff here. There is no appleness according to the moderns. It's what David Hume calls a sense manifold. It's just molecules in motion. Well, where does the idea of apple come from? Well, where do ideas come from? Your mind. So it's the way that you experience. Now, how come we're not experiencing everything differently? Because, going back to Kant, we all share for the most part, the same mental nature, structure. And it operates according to these rules, these laws. If this comes in, then produce this phenomenon here. Sort of like if you ever eat a habanero. Well, how hot do you really want to go? Would you try a ghost pepper? Yeah? That's the thing. The spicy peppers tend to have more flavor, too. Now, you bite down on an habanero or a ghost pepper, and all of a sudden it feels like somebody pulled out a flame torch and was like on your... And now your mouth is 350 degrees Fahrenheit. If you put a thermometer in your mouth, is it going to come out saying something ridiculous like 350 degrees? Dang. Is it really, the pepper really turn your... Well, isn't it something like this? It's simply the sense manifold. Here we got to do a tongue, huh? It's simply the sense manifold, the pepper, the structure of the atoms, which we would know is actually an acid, that if the pepper touches your tongue, then produce what? The phenomena of 350 degrees, right? It's not in the thing. It's here. Immanuel Kant is basically saying that's what space is like. It coordinates everything that's not out there. In fact, Immanuel Kant believes, because he denies essences. Now, it makes the world really easy, because if everything's just molecules in motion, then with his contemporary, there's nothing to consider about nature and essences and teleology. All you have to consider is mathematics in terms of force, vector forces. Everything can be simplified. And that's where you get a lot of success emerging out of the scientific revolution, is you mechanize nature. You get rid of all the other complications, reduce it only to one type of causality, this kind of efficient mechanistic causality, then you can just apply forces in pure mathematics across the board. That doesn't mean that just because something is easier that it's true. What Kant's known for is the Copernican revolution, because Copernicus, as you know, is the one who basically says he doesn't discover it, he posits it. That we're not in a geocentric universe with all the planets. Here's the moon, Mercury, Venus, Mars, Jupiter, Saturn, going around the Earth. He says, what if we change our perspective, Copernicus says, and imagine we were on the sun? Would it look different? Heck yeah, it would. It would look like this. Notice there's a revolution happening, both in the sense of turning over your perspective and also overthrowing the old regime. And therefore, somebody uses this as an analogy. Isn't Immanuel Kant doing the same thing? You used to think that space and time and essences and colors and phenomenon out there that was out there. What's his Copernican revolution? It's in here. There is no essences or anything out there that you even can really know. In fact, I like this. We got to find some of these philosophical action figures. How cool is that? With Copernican revolution, right? His head spins. What was it doing? Spinning. Changing the direction of epistemological fit, having to do with knowledge. How do you know? In the traditional sense, it's the world pressing in. Remember the Aristotelian sense? In causing you to know. World to mind, rather than what Kant does, mind to world. He's flipping it. So that there's nothing out there to experience in the traditional sense. There's no space, there's no relation. Where does that stuff exist? In your mind. They're categories. They're the a priori transcendental categories of apperception, Immanuel Kant says. So when you have all this just particles and data coming in, sort of like if you ever look at clouds, and what do you see? It's like, oh, wow, check it out. It's Achilles. Oh, it's a dolphin. It's a unicorn. Is it really? Are the clouds like, watch this? We'll trip these people out on Earth, right? And turn into a unicorn. Why are you seeing that stuff? It really looks like you'll see faces and stuff in the clouds. You never look at clouds?
Yeah.
So you know what I'm talking, right? I'm not talking madness here, right? It's because you have these facial recognition patterns in your, so that when nonsensical data comes in, what is your brain designed to do? Has like a law-like structure to recognize patterns. It imposes. Isn't that exactly what's going on here? When all this stuff comes into, which is unintelligible, because there's no form in nature. Form was the principle of intelligibility. So what does Kant do? When he denies that there's no forms, he says there's no forms in nature, he realizes that form is still the principle of intelligibility. He saves the day by simply putting the forms in the mind. And there are, unlike Aristotle would say there's 10 categories, Immanuel Kant says there's 12. And they're all subsumed under space and time. Space and time is the transcendental conditions that make perception and knowledge possible, your experience of the world possible. So he's just switched the epistemological causal relation. Instead of the world, the forms coming into your mind, it's your forms in your mind that's making you be able to make sense of the world. And as long as that's regular across the board for each person, that's all we need in a causal structure to be able to say there's knowledge. And by the way, this is an important distinction too. He has something called noumena and phenomena. He actually says the world in itself, the world the way God would objectively see it, is unknown to you. That's the noumenal world. What do you experience? So it's sort of like when you're biting down on the habanero ghost pepper. Suppose you didn't know that it was the structure, the acid, that was making you have this phenomena of hot temperature in your... You're just having the phenomena. You don't know what's causing it. That would be like the noumenal world. I don't know what's in the pepper. Let's say it's not hot temperature, but whatever is out there is producing the effect of having the phenomena of hot temperature. Just sort of an analogy to be drawn there. Now one could ask, well, wait a minute. If I have no access to the noumenal world, why should I think it even exists? Because the principle of sufficient reason. Every effect has a cause. And you don't have to know what the cause is to know that if I'm having the effect, the experience of something, something's causing it. There's a reason for that. For Kant, that's the noumenal world. You have no access to it except in the realm of morality. because morality, he believes, requires freedom. And in the noumenal world that you live in, where everything's push and pulls, there is no freedom. But Kant says we've got to have morality. He says every moral ought implies a can, meaning morality implies freedom. There must be another domain to locate freedom within. That is the noumenal world. That's the only access that you have to the noumenal world, is the moral sphere. Science is done in the phenomenal sphere. So look at the difference between Kant. Both Kant and Newton are contemporaries, and look at the difference between them. Kant believes that space and time are where? Yeah. They are the forms of intuition. That doesn't mean I have a hunch. Intuition is basically like the conditions necessary for the possibility of knowledge and perception. And they depend upon what? The subjective constitution of your mind. The a priori transcendental categories of perception. For Newton, where does space and time exist? They're extramental. They're outside of your mind. And space is conceived to be something like a container in which events can be objectively placed and have absolute reference frame. I bring that up because I had asked you at the beginning of the lecture to think about how do philosophers think about time differently than scientists. Is anybody kind of getting a feel for the way philosophers might think about differently than scientists and physicists? The way that philosophers, I said at the beginning of the lecture, be attentive to the way philosophers think about space and time versus scientists.
Can you define how scientists think of time?
I could, but I don't want to, because I want you to. We'll keep going, and at the end, I'll ask the question again. I'm just getting you to think about it again. So, here's the thing. Isaac Newton based his physics off of a certain type of mathematics. And as you can see, it's geometric. It's Euclidean geometry. Now, that might pose a problem because Euclidean geometry is two-dimensional. What do we mean by dimensions? Mathematical planes to plot out points. So 2 dimensions would be a vertical and horizontal plane like the Cartesian coordinates. So notice I can go up and down. That's 1 dimension on the on the y plane. However, I can go on another dimension, mathematical plane, the x plane. Okay. So I can make things like that, triangles, stuff like that. I can calculate. Now, does that seem a bit strange that how are you going to apply 2-dimensional mathematics? We forgot my tangerine. Spit it up, dude. We need it for as a prop. No, don't spit it up. How are we going to... Well, this kind of looks like a... Okay. It doesn't need to be a spherical object. It just needs to be 3-dimensional. This is something in the physical world, 3-dimensional. Do you think there might be problems of trying to do physics if we are trying to describe a 3-dimensional world in terms of 2 dimensions?
Yeah, because it doesn't apply to the same thing.
Yeah. Euclid had some basic postulates. For example, the shortest distance between 2 points is what kind of line? That's right, a curlicue line. No, I mean a straight line. Also, he had a postulate that given two lines drawn at right angles, therefore parallel lines A, B. So A line is, do parallel lines intersect?
No.
But what if I just keep drawing them out for like a really long time? Won't they? How do you know? Right? Well, Euclid proved, yeah. Thing is, that's two-dimensional. Do those postulates hold true in a three-dimensional world? How am I going to get to Romania? The shortest distance. Am I going to travel on the globe on a straight line? You dig a hole through the center of the earth. That's your straightest line, but that's going to take the longest amount of time. But that's longer, too. What do? You go up. You go up towards Reykjavik. That's why they're stopping in Reykjavik and crossing over Iceland and stuff like that. You make a parabolic arc. So in a three-dimensional world, guess what? The shortest distance between 2 points is not a straight line. It's a parabolic arc. That's why the planes do that. Second of all, take something like this three-dimensional object and try to make parallel lines like that and draw them out. There are scenarios in which parallel lines do intersect because they're laid on top of a three-dimensional object. This is exactly what Bonola argues in non-Euclidean geometry. So we did this in senior year mathematics. It's intense math. It's high-level mathematics. It's once you finish calculus, you start going into, there's many different fields of mathematics you could go into, typology and stuff like that, number theory. But this is non-Euclidean geometry. And why this is so important is it's going to set up for your man Einstein here. And in order to do that, he has to argue that Euclid's basic starting points are false. Why? Because we live in a three-dimensional world, and those postulates don't hold true. And if the postulates and axioms don't hold true, then the whole mathematics being applied to a three-dimensional physical world don't work. It's bogus. We need, in order to describe a three-dimensional world, we need another mathematical plane. So I can draw so I can have cheese wedges, right? So the idea is it's a triangle, but three-dimensional triangle is like a pyramid or a wedge because this is coming out. Now, obviously, it looks weird because I'm having to represent 3 dimensions on a 2-dimensional board. Okay, that gives me space. Space is 3D, 3-dimensional. But Albert Einstein says we need one more dimension. Why? In order to do physics, and physics is not just about 3-dimensional objects, but 3-dimensional objects doing what? Moving. So they can move through space, but then that implies another dimension, which is what? Time. Okay, it looks like, how am I going to do this? I already have the dimension coming out. I have a vertical and horizontal. How am I going to get the 4th dimension, which is time? How am I going to plot that out mathematically? It seems like I've run out of space. No pun intended. There you go. Well, Einstein has something really interesting. On the 3 dimensions, so there's a point there in space, there's a point there. make each point in space also a point in time. This is where relativity begins. Because that means that not only are you in a different point in the space in the room, you're actually at a different time. All of you are in different times. We're not in the same time. And you thought that class started at 1:15. Depends on your physical locale. Does that sound trippy? So time's dependent on space, but each space point time is a different point in time. That's what follows if you have 4 dimensions to, that's exactly. Now, why aren't you experiencing that falling down right there at a different time? Well, because in order for you to see that, if I shut off the lights, would you be able to see the pen falling down? You need light. The light's going to hit this and refract back and hit your eyes. So the wavelengths are made visible by the light hitting you. Do you know how fast light is? 146,000 kilometers per second. Now, if we lined up, let's say, a balloon on the door, and I've got my little airsoft gun right here, and I fire that, yeah, I would have hit. But let's say it's not an airsoft gun. Let's say it's a real gun. I fire that, and the person is hit, or the balloon, instantaneously. At least you think so. Is it really? As soon as I pull the trigger? Well, no. It's just so fast that you can't perceive that it's actually taking time. The bullet's traveling roughly at 846 miles per hour. That ain't got nothing on the speed of light. 146,000 miles per second. To be able to see that bullets, stuff as fast as bullets that are going faster than the speed of sound, are not traveling instantaneous, what do? You create larger distances. So now if I'm out, I'm taking a mile shot or 1,000-yard shot. When I fire that, now when it hits the target, is it going to look instantaneous? It's actually going to take time. That's why you always see in the movies, like with the sniper and stuff like that, okay, the speed of sound is roughly, I think, upward 786 miles per hour, something like that. If you go faster than the speed of sound, the sound is catching up to you. That's why a jet can go by like that, and you don't hear, and then you hear that, right? The sound wave is behind it. It's ahead of the sound wave. That's why when you see in the movie, and the sniper from a long, mile shot shoots the person, right? And the guard, should we make him a Nazi guard or a Bolshevik Stalinistic, right? It's like the video game, right? What character do you want to play? You want to play the Germans or the Russian, the Soviets, or the American, right? Everyone always picks the Nazis because they have the cool uniforms, right? Did you know that? It was who designed their uniforms? Hugo Boss. You didn't know that, huh? You gotta look sharp when you're killing people, right? You gotta look cool when you're going to war, right? So pick your favorite foe. It's the Americans, the Soviets, or the Nazis. It doesn't really matter because you see this where the sniper shoots the foe, the enemy. They go down, and then what happens? You hear and when he pushes you'll have it like 1, 2, bam. Okay, it's taking time. So the way that we can actually tell that light is not instantaneous, very, very long distances. it's going to take time. That's why we talk about light years. There's such large distances. It's a lot easier, instead of writing out a bunch of zeros and zeros, to just simply say, well, it's going to take 30 light years for us to get there, or for the light to get us. Okay, that's one way. Now, because you have these enormous distances, but think about, if Einstein's correct, you are in a different, because you're in a different point in space, you are in a different time. Why aren't you experiencing everything in a different time? Because light's so fast, everything seems instantaneous to you. But if you stretch the distance out long enough, you would be able to tell that time's going to be different according to the place that you are. How am I going to prove that? Using Einstein's theory of special relativity. Here's the whole train. Don't you love trains? Do you know I build model train scenery?
So like hillsides and tunnels?
Yeah, got like my DCC with all the trains running, playing God, right? This town's bad, it's sin, crush it, right? No, I don't do that stuff. But I do build.
Or if you have like a volcano, just erupts.
Right, yeah. I didn't do it. It was the volcano that killed these. Yeah, I created it and I pressed the button to ignite it. Okay, this is going to show how everything is relative in terms of space and time. You're on, let's say we have Janie here and Johnny. And Janie's on the platform as Johnny is traveling at t velocity. Johnny likes to juggle or throw balls up like this. He's bored. Okay. Now, what path does Johnny see that the ball's tracing out in space? Up and down. Okay. That is a motion. That's a vector motion. What happens when I add a second motion to? So I have an up and down motion, but I then do this. Now I'm moving. Now what does it look like?
Like a curve.
Yes. It's making a parabolic arc. Now that's not what Johnny's seeing, because he's moving with the train. So Johnny's seeing this, up and down. The ball or the pan is tracing out a path through space vertically. But he's given the velocity horizontally, while Janie is stationary on. What does Janie see? She sees the parabolic arc. Now ask yourself, well, what is it objectively tracing out? Is the ball actually tracing out a vertical path through space or parabolic? Who's seeing it correctly, in other words? Yes, both. The ball is tracing out both a vertical through space and a parabolic. It depends on your reference point.
But didn't we just say that the universe is like absolute? So there's only...
Einstein rejects that.
Oh, okay.
And in fact, this is the argument against Newton's absolute space. He's saying space and time are relative. How are you going to prove that? Here. If I hold time constant, so that time is the same for Johnny as it is for Janie, space becomes relative. What happens if I hold space constant for both observers? Time will become relative. Watch. This is called the experiment, and it's in the Einstein's book, The Relativity. The relativity of simultaneity. Again, you see things in virtue of light. So if equal distance, point B, or A and B, if two lightning bolts hit at the same time, so notice what do I see? I see them at the at the same time. Why? Because I'm holding my space constant. If it's an equal space to that lightning bolt as it is to there, then if I'm stationary, I'm not moving or getting closer to, while they hit, what do I see? Yeah, I see. Now, have two observers. Although he's moving, when they line up, all distances, because we're holding space constant now. So I need some, even though it's moving, we're going to take a still frame right when the lightning bolts hit so that we can keep our space constant. So from here to here is the same distance from here to here, and those are the same distances to here. So that, yes, you see them stationary at the same time. Whoa. Whoa. Lightning bolt. Got electrocuted. What does the, and now we're going to say, for the sake of the argument, that the said man in train is traveling 3/5 the speed of light. Okay. Make sure you hold the distance constant. Okay, so it's not like he's getting the distance because he's getting closer, that the distance is shrinking. Okay, because you're going to take a still frame right when these two lightning bolts hit. You see them at the same time. What does the person on the train see?
One in the front and one in the back.
The light from A will arrive at X before B. Why? So he'll see, while you're seeing this. Why? Well, that doesn't make any sense because the distance, you took a still frame. That's why I said don't let the distance shrink. You have to hold the space the same. So imagine when the lightning bolt, imagine you're here with the camera and you're like, bam, right when they hit, and the person on the train does the same thing, right when you line up the same space. So at that point, that distance isn't shorter than this. They're all the same. Like I said, you see things because the light travels a certain distance. And it'll take longer the longer the distance is. But the distance is staying the same there. The only thing that's different in this is the motion. He's going really fast, but you're freeze framing it. So that doesn't make sense. Why is he seeing that occur first when you both freeze framed at the same distances? And you see things in terms of how long light takes to... He really shouldn't. He should be seeing this at the same time. Simultaneous. So it's kind of counterintuitive. You like to think like, well, yeah, if I get closer to an object, it's going to hit me. But that's not what's happening. We're holding the space constant in every scenario. So they should be, by supposition, seeing the lightning flashes at the same time. Yes, exactly. This would be, and you wouldn't see that. And this person at the same distance would have two lightning bolts coming down like that. This person would only have this lightning bolt here. Isn't that frickin' weird? Why? Because when you hold space constant, time changes depending on what reference point. Even if you're at the same distances. Why? Because every point in space is also a different point in time. Now, let's do another corollary addendum. It's called the time dilation in the twin paradox. Let's apply. Have you heard of this? Okay, help me name these dudes. Let's say they're brothers. Let's say they're twin brothers. We already used Ryan and Brian.
All right, I'll work it. I can do
Ryan and Brian are born of the same mother on the same day of the same egg, so they're identical twins. But it looks like Ryan has become successful in his career because he's an astronaut, and Brian's a used car salesman. And he's the sperm of his mother's eye, right? Whereas Ryan is the apple of mother's eye. What would mother do? Mother would say, well, Ryan, go out into outer space and explore the mysteries of the universe. And he's saying goodbye to his brother. And he's like, my spacecraft's really fast. It goes the speed of light. He's like, congratulations on, I'm selling you a Buick, right? He's like, look, enough with that. Just set your clock to 1 year. I'll be back in 1 year. Okay, then we'll talk about the Buick. He takes off, going close to the speed of light at least, or the speed of light, and comes back 1 year later to find that his brother's 10 years older, his twin brother. How is that possible?
Isn't it when you approach closer to the speed of light, time slows down?
Time slows down. How do I demonstrate this? Well, you can make clocks based on motion, a regular motion. And the best would be like an atomic clock, the vibration of an electron going back and forth. But you can do it with a pendulum. 1, 2, 3. Or you could even do with a ball. 1, 2, 3. The more regular you can get, the more accurate it would be. So imagine that Ryan and his spacecraft has a laser, a frickin' laser beam. It shoots up, hits the mirror and comes back and hits the receiver and triggers 1 second. 1 second. 2, 3, 4, 5. You made a clock, a counting machine. So just like the ball, while you're moving in the spacecraft, you're going to see the light traveling what? Through space. Traversing a vertical motion here. What is the person on Earth going to see when the spacecraft's moving? Which distance is longer? What's going to take more time? This is going to be perceived. In other words, time is going to be slower for the person here relative to, you're not going to experience, this person isn't going to experience time slower. It's relative to another reference frame. Because for every 1 second, this, suppose, is 3. It's actually going to, I think, be 1 to 10. The ratio. This isn't mapped to scale. So that's when he comes back. He's 10 years older. Although he was experiencing time the same way. They're all experiencing time in the same way, but it's relative to your reference frame. And it changes the faster you go. The closer you get to the speed of light, time will slow down relative to another reference frame. So think about this. Is time something physical? Is it what Immanuel Kant was saying? Well, according to Einstein, time is determined by light. Because nothing can go faster than the speed of light. And also, remember This is kind of space-time fabric here. But really, it's less like a fabric and more kind of like a three-dimensional fabric, like a jello mold or something like that. So that means if you placed a mass object into the fabric or the jelly mold, what's going to happen to it's going to push out. It's going to, just like this. It's going to bend space-time. Now think about this. Time is determined by the speed of light. It takes time for the light. If the sun blew up, you wouldn't see it for what? 8 minutes. But it's not that you're just not perceiving it, because it's going to take 8 minutes for light from the sun to hit. That's an extreme distance. But light's so fast that it will take 8 minutes to. Now, here's where relativity gets really trippy. It's not that you're just experiencing time differently. The time is different. In other words, from the sun's reference point, if you were at the sun, it blew up, it's clearly blowing up and you're dying. Okay? If you could go to the sun without burning up, which is why smart people say you just go to the sun when it's nighttime. Wonk, wonk, wonk. If you're on the sun, it's obviously happening instantaneously. But guess what? If you're on the earth, not only do you not see it for 8 minutes, it hasn't happened. All of reality is determined by the speed of light. It's on the edge of the speed of light. So that image traveling through space and light of the sun blowing up has not happened until that light gets to Earth. Isn't that amazing? Sorry, I got it wrong. I said 146,000. It was 186,000 miles per second, or 300,000 kilometers per second. I know, right? So there is reality. It's blowing up. It hasn't happened yet. Not that you haven't seen it. Both. You haven't seen it, and because you haven't seen it, it hasn't happened. It's traversing. Isn't that crazy? So that means if you could go faster, if reality and time is determined by the speed of light, and you know the faster you get closer to the speed of light, the more time slows down. If you could go faster than the speed of light, you could get to space-time points before they happened. In other words, if you could travel faster than light, you could go back into the future. Remember, the sun blowing up has not, when you're on Earth, it has not happened for another 8 minutes. If you build a rocket ship that goes the speed of light, or faster than the speed of light, you could get ahead of the 8 minutes and stop that thing from blowing up. Isn't that crazy? You can time travel. Theoretically, you can time travel. But you can only travel into the past because, remember, there's nothing on the other side of light, i.e. the future. All you could do is what's in the past. Because once you see the sun blowing up from the point in space of the sun, it's gone. That's the past. So if you could get ahead of the speed of light, you could get to that space-time point before the sun blows up. Not only from your reference point, but from the sun's reference point as well. Because reality is being determined by light, the speed of light.
Like how we see like a star blow up in the sky, like when we see that it's already blown up.
Yeah.
It's already happened.
Yep. That's why I say when you're looking into the past. You see a supernova here, it's gone. If you could actually capture a supernova, which I think they've done a few times, that's happened millions of years ago. If you really could go over there fast enough, it wouldn't be there. I mean, it takes that long. So most of those stars aren't even there. You're just seeing the after effects of, just like this. My clapping. Okay. Notice that hits the walls. Does it hit instantaneous? No. This happens first, then that. You're experiencing the effects of, well, light's a wave as well. So when you see stuff, because everything's a different time point space, it's already happened. You think it's instantaneous, you think you're looking at stars, they're gone. They're not even there. Most of them. Isn't that amazing? Now here's the problem. Here's the clincher. Nothing can go faster than the speed of light. So how could you time travel? Well, remember you have to go faster than the speed of light. Well, here's the thing. Everything on the space-time fabric is a space-time point. And notice the heavier mass that I put, the more it bends that. What if I could bend it enough to bring 2 points in space together? Yes, it's called a wormhole. Because space points are also time points. Different points in space are different points in time. Now, there would be an object blocking that. That's why if you have a sun becomes a red giant and then explodes into a supernova, if it's large enough, if it has a large enough mass to bend space-time enough, when it blows up, there's still an imprint on space-time, and i.e. there's still gravity there, strong gravity. If it were strong enough to do that, you'd create a black hole. What is a black hole? It's gravity with no object there. Well, how do you detect black on black? Because space is black, and they're saying there's a black hole. It's like, how do you know that? How are you going to be able to visually detect a...
Stars warp around it because the gravity is so intense at black holes that it actually even warps light away.
Yep.
Light even can't escape black.
Let me go back to... We'll obviously you want to finish the lecture on Monday because we're obviously not going to get through... Because there's a lot more cool stuff, too. See how this is bending here? Light travels along here, it's going to bend like that. Now you can see it bending around planets. Now what happens when there's no planet and you see light bending? Gravity must be bending it. What is gravity? And by the way, this was conceived to be a better scientific theory than Newton's theory of gravity. Newton's theory of gravity is that objects like the Earth, the moon is being acted upon from a distance. That sounds like sorcery. If I start doing this and moving objects without touching them, you'd be like, he's into the occult. That's exactly what they accuse Newton of. You're introducing occultic properties into science. Would be nicer, why is the moon being pulled into the Earth? Now, it doesn't fall into the Earth because it's given another velocity. But look because if you rolled a marble, if you did this, it would go in. If you give it another velocity, it's going to want to come in, but it's got another velocity to do this. That is physically a better theory within science, and so that was appreciated. And it also is going to help him explain how light can curve along the space-time. But yes, if it curved enough and there was no massed object to bring two space-time points together, if you walk through the wormhole guess what? You walk into the past. You walk into a different point in time. So there you go. I just told you how to do time travel. Go build your time machine.
It's puzzling. I don't think I've ever seen anything quite like this before.